In this module of the ACI multi-site training, we're going to look at the network services integration with ACI multi-site. First, we will discuss what are the integration models for network services integration with multi-site, and then we'll look into the specifics of how network services integration can be performed to handle north-south and east-west traffic flows. Let's start with the discussion about the integration models. The two common deployment models for network services are what we define them as cluster, active standby cluster or active-active clusters. Now, as you see in the slide, these two deployment models, so deploying a cluster of services across different ACI fabrics or ACI networks, are typical deployment options that are fully supported with ACI multipod. But with ACI multi-site, we have limited supported option when deploy an active standby pair across different fabrics. And specifically, we saw during the previous module of the ACI multi-site training that we could deploy an active standby pair connected to the L3 out when enabling the inter-site L3 out. We could also deploy an active standby pair of firewall when deploying the firewall as a default gateway, so when ACI only performs layer 2 functionalities. But for example, it's not possible to use Service Graph with PBR having an active standby pair of nodes deployed across independent epic domains. For the active-active cluster, the model is pretty much not supported with multi-site. And this, if you think, makes quite sense because deploying a cluster and stretching a cluster of services across different ACI networks means essentially that these different ACI networks are operated like a single logical data center, and that's why multipod would be the right architectural approach to support that integration models. With multi-site, the assumption is that each fabric part of the multi-site domain is an independent network with its own epic domain, but also with its own set of network services. That's why the recommended deployment model for ACI multi-site consists in deploying independent network services instances in the different sites. And when we do this, there are a couple of deployment options that can be supported. One we already discussed in the module where we described the connectivity between multi-site and external layer 3 out network, and we saw that we can support independent active standby firewall pair deployed as perimeter firewall when enabling, for example, host-based routing and preventing the creation of asymmetric traffic path. The focus of this section is actually to talk about how to deploy independent network services in each fabric and show how the multi-site architecture has been designed to ensure that when deploying Service Graph with PBR in a multi-site deployment, the architecture itself takes care of avoiding the creation of asymmetric traffic path across these separate service instances. Before going into the details of how things work, some high-level design consideration for this use of Service Graph and policy-based redirection with multi-site. First of all, the PBR policy applied on a leaf switch can only redirect traffic to a service node deployed in the local site. So we do not support applying a PBR policy on a leaf in site 1 to redirect traffic to a service node which is connected to site 2. Okay? So the assumption is in each site there must always be a local service node function available, which essentially means that we need to ensure that the local function is deployed in a redundant fashion. And we will see in the next slide what are the options to ensure that. Second, there are hardware dependencies. When deploying Service Graph and PBR with multi-site, we mandate the use of EX or FX leaf nodes, or newer, right, GX, FX2. So second generation for both the compute node where the endpoints are connected and the service leaf node where the service nodes are connected. In terms of software, the integration of service node with multi-site using Service Graph and PBR has been supported from the release 3.2, but the recommendation is to look at that only starting from release 4.0 because, as we will see, we change the point of enforcements of the PBR policy in that release. So to have a consistent behavior, is good not to mix 3.2 and 4.0 releases. As I mentioned, since the PBR policy applied on a leaf in a site can only redirect traffic to a service node deployed in that site, we need to ensure a resilient service node deployment in each site. There are different options for that. We could deploy an active standby pair of service, like in this case firewalls, in a site. That's a typical high availability deployment model, which ensures that when the active firewall fails, the standby takes over and redirection start happening to that standby node newly activated. If I want to have more bandwidth, more resiliency, I could actually deploy an active-active cluster in a fabric, which can actually be built when using the Cisco Firepower firewall with up to 16 nodes, part of the same cluster, where all these nodes are bundled together to look like a single logical firewall. In this example, I have 4 nodes clustered together. I can lose one of the nodes. I still have 3 active nodes that perform my logical firewall function. Okay, so more resiliency, more throughput. The third model could be to deploy independent firewall inside the same fabric. And while in the previous 2 models, the PBR policy would always redirect to a specific IP MAC because logically I have a single firewall in both the active standby and active-active cluster mode. With this third option, the PBR policy will need to basically redirect to different MAC IP pairs, right? Each one representing the independent firewall that is deployed in the fabric. And we will leverage symmetric PBR to ensure that the redirection that happens for a given traffic flows between 2 EPG selects the same firewall node in both directions of the traffic, right, to avoid the creation of asymmetric traffic path. So symmetric PBR is key when I have independent active nodes and when I create a PBR policy with multiple nodes in it. So these are 3 options to ensure that we create a resilient service node deployment inside each ACI fabric, part of the multi-site domain. Now, when we talk about the deployment of service graph with PBR, in general, we can have a single node service graph where I have an EPG client and EPG server and I apply a contract. I attach a service graph to that contract that says I want to redirect the traffic between these 2 EPG to a firewall node. This has been supported with multi-site from 3.2, but as I said, we recommend the deployment of this starting from the 4.0 release because we change the point where the policy is applied to be always on the provider leaf. And we will clarify this better in few slides where I show you how this actually works. Another option that we have been supported as a single node service graph is the one where I want to stitch a load balancer between the client and the server. Now, in this case, there are 2 scenarios. The scenario I show here, where the load balancer performs as NAT, doesn't even require to use PBR. Why? Because traffic client to server is always sent to the VIP of the load balancer, and so we just route to the VIP. And then when the load balancer sends the traffic to the server farm, it will perform source NAT, so it will replace the source IP address with one IP address that he owns. That means that the return traffic from the server to the client is always going to be stitched back to the load balancer because the load balancer is going to be the destination. And this is thanks to the asNAT function. So integrating this requires the creation of a single node service graph, but no PBR function is needed. The PBR function is instead needed, but only for the return traffic between the server farm and the client when the load balancer does not perform source NAT. Because in that case, I need to ensure that the traffic returning from the server farm is not sent directly to the client, but is stitched back to the load balancer. Okay, so I apply PBR in that direction only. So these 3 models have been supported from 3.2, but as I said, we recommend that you deploy it from 4.0. There are also models where we have a dual node service graph with PBR that can be deployed. So I could have, for example, a service graph with 2 nodes, the firewall and the load balancer. Now, in this case, again, we have 2 scenarios. If the load balancer can do as NAT, and that's a deployment model that is desired, then the PBR is actually done only to the firewall. We don't need to do any PBR to the load balancer for the reason I mentioned before. This has been supported from ACI release 4.0.1. The other deployment model is the one where the load balancer does not perform as NAT. And in this case, from the client to server direction, we need to have only one PBR redirection to the firewall, because then traffic will go to the VIP of the load balancer. But the return traffic from the server farm to the client will go through two PBR redirection. The first one to send the traffic to the load balancer, and then to send the traffic to the firewall. Again, this is also being supported from ACI release 4.0.1. Let's now look more specifically how to integrate Service Node to handle North-South and East-West traffic flows. Some best practices for this: the Service Node can be deployed in one-arm mode or in two arms mode. The deployment in one-arm mode, as I show in this picture, where basically I have a single interface on the Service Node connecting to a service BD, it's advantageous because it simplifies the routing configuration on the Service Node itself. I can just have a single default route on the Service Node pointing to the default gateway being the IP address of the service BD in ACI. And I don't need to worry about creating more complex static routing configuration. In addition to that, the service BD must be stretched across the sites. That's a mandatory requirement. Now, you can stretch it in the smart way, so without bump forwarding enable, but it needs to be L2 stretch. The service BD needs to be L2 stretch. The external EPG for North-South needs also to be a stretch object that then can be mapped individually to the L3 outs defined in each site. And we discussed this already when talking about the communication between external network domain and multi-site. The web and app or the server and client EPGs, whatever you want to call it, can actually be stretched or can be locally defined objects. So we are flexibility around that. Two more important points. For North-South flows, we currently support only intra-VRF Service Graph and PBR redirection. Okay, so the external EPG, the L3 out, and the internal EPG needs to be part of the same VRF and tenant. For East-West use cases, we actually support also inter-VRF and inter-tenants contract. And the other important point is that in order to deploy East-West service integration, we need to configure the subnet under the consumer EPG. And so that means essentially it would be a problem to deploy this East-West network services integration model if I had an application-centric deployment, because if I have multiple EPG part of the same subnet, it would not be possible to apply the subnet under the specific consumer EPG. Okay, so in the current implementation, it's a deployment model that works for network-centric deployments. Let's now look how this actually works, starting from the North-South communication. So the first thing I would do to enable this functionality, I go on the multi-site orchestrator and I create my contract, in this example between external EPG, which as we said needs to be a stretch object deployed across sites and map to each L3 out in each site, and an internal EPG, my web EPG. In this example, my web EPG is a stretch object with its own bridge domain, so is extended across site 1 and 2, as you see here. When I apply the contract, I also specify on the multi-site orchestrator that the contract needs to be associated to a service graph, which I also created on the multi-site orchestrator. So when I do that, traffic, as we said already in a previous module, destined to the subnet 10.10.10 could be sent to the L3 out of site 1 or to the L3 out of site 2. Let's assume there is no host route advertisement deployed for this example. Deploying host route advertisement will be an optimization in this case, but we will see that things will work even if you don't do that. So if the traffic destined to the 10.10.10.10 is directly to the L3 out in site 1, then the border leaf will not apply policy by default, and this is the default behavior when you have the policy controls enforcement direction set as ingress, which is the default configuration for the VRF. And it's important not to change that, because for North-South traffic, we need to ensure that the PBR policy is always applied on the compute leaf node where the destination endpoint is connected. So you see here the traffic comes in, the border leaf does not apply policy, but just forward the traffic toward the leaf where the destination is connected. When the leaf gets the packet, the destination is directly connected, but I cannot send the traffic directly to the destination because I specified in my intent, in my contract, that I need to redirect the traffic to a firewall. So the traffic will be redirected based on the PBR policy to the local firewall. As here we assume that we have deployed an active standby pair in the fabric, but we saw before we have different redundancy models that can be deployed inside the fabric. The firewall will do its job, will apply its policy, and then will send the traffic back into the fabric, and the fabric will deliver the packet to the destination endpoint. The same exact thing will happen if traffic was to come in the L3 out of Site 1, but destined to an endpoint or part of the stretch EPG located in a remote site. So the border leaf and multi-site will do their job and deliver the packet to the compute leaf in Site 2, in this example, where the destination endpoint is connected. Once the traffic reach that leaf, the PBR policy will be applied and will redirect the traffic to the local firewall service. So you see that the firewall that is used for each flow between the external world and the internal EPG always redirect the traffic to the service node, which is deployed in the site where the internal destination endpoint is located. Once the traffic comes back, so the response from the internal endpoint toward the external world, the same thing happened. The policy is always applied on the compute leaf node. So when 10.10.10 replies, the traffic is redirected by the directly connected leaf to the firewall. The firewall does its job, sends the traffic into the fabric, and the fabric then delivers the packet to the external destination. The exact same thing happens for the endpoint inside 2. So you see that for the endpoint in Site 2, the inbound traffic was received on the L3 out of Site 1. The outbound traffic leaves from the L3 out in Site 2. So we have a sort of asymmetric behavior from the point of view of which L3 out I'm using, but from the point of view of the service node that is used, which is the important point because that's the stateful device, we always use the same firewall, the firewall in Site 2. Okay? So you see how for NorthSouth, the architecture itself takes care of ensuring that you will never create an asymmetric traffic path across two independent firewall nodes, which is what would happen if you were to connect the firewall to the L3 out as perimeter firewall and not enable host-based routing. Okay? Let's now consider the scenario of east-west communication. So basically the insertion of a service node for traffic flows between endpoints that are part of EPGs that are deployed inside the fabrics in different sites. We want to be able to support this service insertion between EPGs that can be either locally defined in each site, like in this example that you see here, or even stretch across sites. So we need to support both combinations. And also these EPGs can be part of the same VRF or also in different VRFs and or tenants. And the main difference between this scenario, east-west use case, compared to the north-south that we just discussed, is the fact that in the north-south case, we said that we ensure that the PBR policy was always applied on the ACI leaf where the internal endpoints was connected. And this ensured that we were not creating a symmetric traffic path because the firewall that was used was the one in the site where the internal endpoint was connected, always, for both directions of the flows. Now, for east-west, all the endpoints are internal, so I cannot distinguish anymore external endpoint and internal endpoint. So we need something else to ensure that the PBR policy application can be anchored on a specific fabric, on a specific site. And we leverage for that the concept that each contract always has a provider and a consumer side. So in this example, I want to apply a contract between my web EPG and my app EPG. The web EPG is the provider of the contract of the service, and the app EPG is the consumer. I go on the multi-site orchestrator, I define my contract, I attach a service graph that I define on the multi-site orchestrator, and I do an additional configuration steps that consist in specifying the subnet for the consumer EPG under the consumer EPG itself. Defining the subnet under the consumer EPG provides two values and two functional reasons for doing that. One is allow us to install on the provider leaf the subnet of the consumer EPG, so that when the packet is received on the provider leaf knows how to route traffic to the consumer endpoint. But more importantly, together with the subnet, we can install on the provider leaf also the PC tag or the class ID identifying the consumer EPG. So not only I have routing information, but I also have policy information that ensures that I can always apply the PBR policy on the provider leaf. So if the web EPG starts the communication to the app EPG, the packet is received by the leaf where the web EPG provider endpoint is connected. That is the provider leaf. Because of that configuration under the consumer EPG that I just described, we have routing and policy information, so we can apply the policy, the PBR policy, directly on the provider leaf. So traffic will be redirected to one of the firewall nodes that are deployed in Site 1. The firewall will do its job, send the traffic back to the fabric, and then multi-site will do its task of delivering the packets to whatever remote fabric the consumer endpoint, the app EPG endpoint, is located. In this example, in Site 2. When the app EPG replies back, we do not apply the policy on the consumer leaf, because if we did that, the packet will be sent to the firewall in Site 2, creating an asymmetric traffic path. So we do not apply the PBR policy there, in virtue of the fact that we don't have information for the provider EPG on the consumer leaf. So the traffic is just going to be forwarded by multi-site, reach the provider leaf in Site 1 where the destination endpoint, the web EPG endpoint, is connected, and at that point the PBR policy will kick in again and will send the traffic to the local firewall that receive the first leg of the communication. This ensures that the two legs of the communication between the web EPG and the app EPG are sent through the same firewall located in Site 1. Okay, so the rule for east-west communication, for services insertion, for east-west traffic flows, is that we will always use a service node in the site where the provider endpoint is connected. And the key to allow that to happen is to configure the subnet under the consumer EPG, which basically also means that this works very well in an application-centric approach where I have one EPG per BD per subnet, and not when I have multiple EPGs part of the same bridge domain. This ends the module of the multi-site training talking about service insertion with multi-site. Thanks for watching.